Hi, I'm Darren and welcome to Level Up EE Lab. I recently did a video on my HG10 VFO and there was one more measurement that I wanted to make on the signal output, but I lacked the tool at the time to do it. Today I've got an idea of how to make that tool, and that's what I'm going to be talking about in this episode. So let's get started. In my recent Heathkit HG10 VFO episode, I examined its funky output waveform using my oscilloscope. By design, the waveform is not a pure sine wave. Instead, it's rich in harmonic content. It contains integer multiples of its fundamental frequency, which are then selected by rigs like the DX60 for driving an RF transmission on a specific amateur HF band. I really wanted to examine that waveform on my spectrum analyzer, mostly so I could see just how strong those harmonics are, plus look for any out-of-band harmonics. But there was a problem. Spectrum analyzers like my Tiny SA and my home brewed model have very low input impedances, 50 ohms. However, the specifications for the HG10 require terminating it into a load of at least 1,000 times that, which made me concerned that the HG10 might have an output impedance much higher than 50 ohms. If I attempted to measure it anyway, assuming my spectrum analyzer could handle the peak voltage coming out of the HG10, it would have definitely presented a heavy load to the output. Now that would cause the magnitudes of all the peaks in the frequency domain response to be reported too low. In worst case, it may have even added additional distortion that's not present in the output normally, and it may have even caused the output to cease working on the HG10. Let's look at the output stage of the HG10 and try to figure out why Heathkit states to use at least a 50K load. It's a design called a cathode follower, a very common vacuum tube amplifier that has a high input impedance and a low output impedance, typically much lower than 50K. A ballpark estimate for a cathode follower output impedance can be made just by taking the inverse of the tube's transconductance, or G sub M. According to the Sylvania datasheet, the tube used here, a 6CH8, has a typical G sub M of 3300 micromhos for the triode section. Now G sub M does vary based upon the actual plate voltage and the current, but a typical value is good enough to get me in the ballpark. The inverse of 3300 micromhos is 303 ohms. So why does Heathkit say to connect more than 50K? I think an important factor here is Heathkit's choice of the DC blocking capacitor on the output, C30. It's 100 picofarads, and together with whatever load resistance you connect, you'll make a high-pass filter. With a 50K load, there's no concern. The filter cutoff frequency would be very low, around 32 kHz, and that's well below the HG10's lowest output frequency. But reduce the load to 300 ohms and that cutoff rises to 5.3 MHz. And at 50 ohms, the impedance of my spectrum analyzers, it's at a whopping 32 MHz. So that's a concern. Low impedance loads connected to the HG10 will greatly attenuate the signal magnitude. Now, of course, because Heathkit marketed the HG10 to work with rigs like the DX60, it's clearly intended to be connected to a high impedance load. Just look here at the DX60 input circuit. The VFO input goes directly to the control grid on the 6CL6 tube, which then presents a high input impedance, and therefore the voltage level of the HG10 output will be maintained, which is important to properly drive the 6CL6 tube. So there's my dilemma. If I want to take a look at the output of my HG10 with any of my test equipment that has a 50 ohm input impedance, I'm going to need a tool. Let's call it a probe that makes that input impedance appear to be much higher and therefore will give me believable results. This is actually a very common problem in engineering and in science called the observer effect. Essentially what it means is our attempt to measure a phenomenon actually ends up altering the normal behavior of that phenomenon so much that we can't trust the results. A crude solution for this observer effect would be just to add some series resistance ahead of the SA input. For example, putting in 950 ohms of series resistance boosts the impedance the circuit sees to 1 kiloohm. With that 100 picofarad output capacitor, our effective high-pass filter now has a cutoff of around 1.6 MHz. Not a big issue considering that our lowest frequency is 3.5 MHz. However, that 950 ohms of series resistance drops the signal at the SA by 26 dB. That's painful, but there still might be some useful information left. Passive probes that incorporate 950 ohms of series resistance are commercially available. Tektronix made a probe just like that, the P6158. It's called a 20 times probe because it divides the signal input voltage by a factor of 20, or 26 dB. It also has very low parasitic capacitance, only 1.5 picofarad. Now that's critical for AC performance. Higher parasitic capacitance will limit the maximum useful frequency. It does pass DC though, so you'd need to insert a blocking capacitor between it and your 50 ohm equipment, which is right back to adding high-pass filtering that might be undesirable. Unfortunately, it looks like Tektronix stopped making it a few years ago. You can pick up a used one, of course, but even used ones still run for several $100. Not cheap. There are a few competitor options, but a quick search makes it obvious that these types of passive probes are just not that common. What about just using conventional oscilloscope passive probes? Well, a 1-to-1 probe, of course, would just pass through the 50 ohm impedance of the SA, along with lots of cable capacitance. Not good. A 10-to-1 probe won't work either because it's a combo of DC and AC voltage dividers designed to work with the scope's input, 1 megohm and several tens of picofarads typically, and that's not at all what an SA has. Also, both the 1X and 10X probes will pass DC, so we're back to the blocking capacitor issue. So that gets us to the more common solution used today, and finally the main subject of this episode, the active probe. Essentially, this probe puts a buffer amplifier between your high impedance circuit and your low impedance test equipment. In effect, the active probe disguises the low impedance and keeps your test circuit from seeing it or being affected by it. A really good active probe will have a flat response over a high bandwidth. The flat response comes from having a very linear buffer amplifier, one that doesn't attenuate or amplify the signal appreciably over a wide frequency range. The high bandwidth mostly comes from having extremely low input capacitance, something on the order of a picofarad or even less. And of course block DC from appearing at the output so we don't harm a typical SA. Now, not surprisingly, active probes with all of these nice features do not come cheap. For example, here's this really nice Keysight 41800A, which features a bandwidth up to 500 MHz, a megohm input impedance with only 1.5 picofarads of capacitance, and a really flat frequency response. It also features a whopper of a price. Brace yourselves, almost $7,000 new. For hobbyist applications, I certainly don't need something as ridiculously expensive as that. It's definitely doable to make your own active probe that'll still be useful in the home lab. Now, I'm not nearly clever enough yet to design my own active probe, so what I've done is scoured the internet and I've turned up 3 publicly available designs that, number 1, I understand how they work, and number 2, I think I can build. The first is this classic Bob Pease circuit. Basic specs are a claimed input impedance of a colossal 100 gigaohms, an input capacitance of well below a picofarad, and a bandwidth of around 90 megahertz with essentially unity gain. Because the output stage is an emitter follower, the output impedance will be very low. So it should be fine to use it with either a 1 meg scope input or a 50 ohm SA input, of course with a DC blocking capacitor. The 2 FETs are spec'd as a 2N5485 or 5486, neither of which are manufactured anymore. However, I found that the surface mount equivalents are still available. This design does need both a plus 15 and a minus 15 volt power supply, which is doable, but a bit of a pain to set up. Next up is this simple design by David Jewsbury. It's built around a dual gate FET like the BF998. The input capacitor C1 is a gimmick capacitor made from the PC board foil and is less than a picofarad. Networking it with the low input capacitance of the BF998 yields a claimed input capacitance of 0.75 picofarad. R1 and the naturally high input impedance of a FET keeps the input resistance at around 10 meg. Advantages include needing only a single-sided supply, and the design does have a built-in linear regulator. Claimed bandwidth is impressive, 1.5 gigahertz. Now that's much more than I need for my hobbyist work. And the output impedance is set to 50 ohms. Now some disadvantages. The biggest one is the FET itself. 20 years ago when Dave published this design, dual gate FETs were plentiful. But nowadays they've all but vanished from series production. I could not find singletons available through distribution, so I decided to take a flyer and buy 10 of them off eBay. Yikes. Another disadvantage of this design is loss. C1 plus the FET input capacitance and the small loss that you get in a source follower amplifier all adds up to around a 20 dB loss. And lastly, probe design number 3. This is a 2005 design by Steve Hageman. It's built around the OPA 656 op amp, which is a high-speed FET device made by TI with active probes listed as one of the target applications. Or at least it was made by TI. It's now obsolete, but fortunately there is a suggested newer replacement, the OPA 814, and it looks like it'll work just fine. The rest of the circuit consists of an input filter network, a pair of overload protection diodes, and a feedback network to set the output gain at 1:1, along with this 51 ohm resistor to set the output impedance. Performance is specified by the author as, quote, an inexpensive and well-protected unity gain probe that presents the same input impedance as a basic bench oscilloscope. So from the perspective of the circuit you're trying to measure, it'll look like a 1 meg resistor in parallel with 15 picofarads of capacitance. Not the best of the three, but likely still very useful. Okay, so which one of these three am I going to build and test? Well, to paraphrase a favorite line of mine from the movie Contact, why build one when you can build three at 3 times the price and effort? So that's exactly what I'm going to do. I'm going to build them all. They're not that complicated, and in fact, as I stand here recording the ending for this episode, I've already chosen a fabrication direction. I'm going to use a piece of 1/2-inch diameter brass tubing, cut the length for the probe body. That'll also provide some shielding for the probe circuitry, and then make some skinny circuit boards to fit right inside the tube, and design and 3D print some end caps for the terminations and the cables and the wires that come out. So it's going to look like the little brother of the Mr. Carlson Super Probe. This is my version of it that I built a few years ago. So it'll be pretty rugged. I've already got 2 of the 3 circuit boards etched and populated, and they fit nicely right inside the tubing. So like I say, I'm already pretty far along. I'll be going through those details along with some LT Spice simulations of predicted behavior and compare it to actual behavior in the next episode. Hopefully those two will align pretty well. As always, I hope you guys are enjoying this material and enjoying my channel. So until next time, bye for now.